Okay, so we're going to be looking at solving the Bernoulli equation dy by dx is equal to y plus 1 over y, subject to the given data y of 0 is equal to minus 1. In other words, when x is 0, y takes the value minus 1. So the first thing we do is rearrange this equation to get it of classic Bernoulli form. So we get all the dy by dx's and all the y's on one side and the power of y on the other side. We have dy by dx minus y equals y to the minus 1. So this is of classic Bernoulli form. The n in this case is minus 1, it's the power of the y on the right hand side. So we introduce a variable v to be y to the power of 1 minus n. And this means of course that v must be equal to y squared. We now convert our Bernoulli equation from y's and x's to a differential equation involving v's and x's. To do this, we need to express dy by dx in terms of v. Well, dv by dx is equal to dv by dy times dy by dx. The dy's cancel. And of course dv by dy is nothing more than 2 times y. So this means that dv by dx must be equal to 2y times dy by dx, which rearranges to give dy by dx is 1 over 2y times dv by dx. We now take this expression for dy by dx, put it into our differential equation for y, and we can see that we obtain 1 over 2y times dv by dx minus y is equal to 1 over y. Now we rearrange this equation by multiplying through both sides by 2y to see that dv by dx minus 2y squared is equal to 2. Now let's remember that y squared was what we defined to be v. So let's replace the y squared by v to get dv by dx minus 2v is equal to 2. So what we've got here now is a first order equation for v that can be solved using the method of integrating factors. So the integrating factor is defined to be the exponential of the integral of minus 2 in this case. In other words, that's the exponential of minus 2x. So we multiply both sides of our differential equation for v by this integrating factor. We get e to the minus 2x dv by dx is equal to, minus 2 times e to the minus 2xv is equal to 2e to the minus 2x. Now of course the left hand side is always the same as the derivative of the integrating factor times whatever function is being differentiated in the differential equation. In this case it's v. So the left hand side is the derivative of v times e to the minus 2x. So now if we integrate both sides, we see that v times e to the minus 2x must be the integral of 2 times e to the minus 2x. And the integral of 2e to the minus 2x is minus e to the minus 2x plus a constant c. So we can now rearrange this expression to come up with the form for v. We do this by multiplying both sides by e to the 2x. When we do that, we get that v is equal to minus 1 plus c times e to the 2x. Let's now recall that v was defined to be y squared, so to get y we have to take plus or minus the square root of v. If we do that, we see that y is plus or minus the square root of c times e to the 2x minus 1, and this is our general solution to the Bernoulli equation. Now, let's apply the given initial data to construct our particular solution. So we saw that when x was equal to 0, y took a value 1. So let's substitute in for x is 0 and y is minus 1 into our general solution. So when we do that, we see that minus 1 has got to be plus or minus the square root of c minus 1. This tells us a couple of things. First of all, it tells us we have to take the negative root. There's no other way we can get a negative number otherwise. Moreover, it tells us that c then has to take a value of 2. Hence, we can take our initial data and then construct our particular solution to the Bernoulli equation. And it's y equals minus the square root of 2e to the 2x minus 1.